computer. Okay, great. I see we have people all over campus and in various places on campus, so that's great. All right, welcome back, everybody. This is Organic Chemistry 1. I'm, of course, Dr. David Irvin, and we'll begin with what's due this week. So I looked at the tentative schedule for our modules and stuff, and so it says we were supposed to be doing Module 3 last week, but we're going to do Module 3 today. And so that's acids and bases. And the last module we're going to do before our exam is Module 4, which is cycloalkanes and conformations of alkanes. I've uploaded those slides to Canvas and to Top Hat. So those are the most updated slides that are available for that. So the acids and bases, as well as the cycloalkanes and stuff, are all uploaded. And those will be the last 2 sections we do before our exam on September 25th, okay? We are gonna have a review on the Wednesday before the exam. And remember that we're also gonna have mock exams on Monday, Tuesday, and Wednesday to make sure that your electronics are working correctly, okay? The last thing we're gonna do before that is I'm gonna do Module 3 today. On Friday, we're gonna have our nomenclature class group project, okay? So there's gonna be 2 components of that. I've mailed that out today. I believe you should have all received it. The page 1 is basically you're going to be naming it, and this page 2, you're gonna be drawing it. So you're gonna get practice doing both naming and drawing. At the end of the activity, you're gonna go ahead and scan it in or take a picture and upload that to Canvas. I'll put a tab on Canvas there, so we'll have that available to us. And then Module 4, I'll actually complete on Monday, the 21st, and then we'll have the review of all the different things, you know, nomenclature, functional groups, and I'm working up a mnemonic to try to figure out how, you know, how to keep those different functional groups in order. I should have that by our class on Friday. I'm trying to get a cool way to get those to easily remember the order in which that is. Okay, will we have a study guide for the test? Do we know how many questions the exam will have? And will we have class time to take it, the exam? Yes, the entire class on Friday, September 25th will be the exam, okay? So you don't log into Zoom, you just go to Top Hat, the exam will open up at 10 a.m. You'll have the entire hour to take it. There should be 25 questions on there, and they're all multiple choice. Okay, so because I would normally have a writing component on there, that's why we do the group activity, so you get to practice writing. And so that when we have the online exam, it's only going to be multiple choice, okay? Because that's the easiest way to do the monitoring. And so again, with the mock exam, it'll have a video monitor system. I never look at the videos unless it comes up as extremely suspicious, you know, and then it has AI, artificial intelligence actually scan these things. So what you'll need for that is an ID, and you'll show your ID, kind of show that you're alone in the room or that there's nobody there trying to give you answers, and then it'll kind of lock out all your other screens. Again, I'll send you those instructions on Monday, and so that when we'll have our mock exam, you can prepare by doing those particular processes that they recommend. Okay, does that answer everybody's question about the exam? Okay, so well, what's due this week, of course, is that our Module 2.2 homework is due at midnight tonight. Okay, that's just the IR. And Module 3 homework will be due Friday night. We're going to do Module 3 today, and we're going to do the activity, and I can answer any questions about Module 3 from now till Friday. And then we will go ahead and do that Module 4 on Monday, as well as a mock exam. Okay, we will be doing the exam as an online Top Hat proctored exam. So you must go ahead, and that's why we're going to do those tests next week. Make sure you have Proctorio loaded into your Google Chrome. You must have Google Chrome, you must have Proctorio, and you must have a operating video camera. Okay, and I'll send out all those instructions over the weekend, and we'll have our first mock exam available to us on Monday. It's just gonna be 5 questions, what's your favorite color, kind of stuff like that. Just so that you can get the idea of how to answer questions and how to submit the exam when you're done, okay? All right, let me take a nice drink of water here. All right, are those all the administration questions? Okay, well, I'd like to share my slides for Module 3, okay? Okay, let's see, I had a question in the chat here. Are we allowed to have with us on the exam? I'm trying to get it so that you don't need anything for the exam, and I'm trying to get an access to a periodic table that you can use as on Top Hat. So all you'll need is your computer and some scratch paper, and that's it, okay? Okay, so here we have our slides up there for Module 3 in acids and bases. And you're thinking, oh, Gen Chem, I had to calculate pH and buffers and all that stuff, and it was really, really hard. Well, in organic chemistry, what we're focusing is on 2 specific aspects of acids and bases, and we have a slightly new definition for acids and bases that I want you to use. This is the most important definition of acids and bases we use in organic chemistry, okay? And it's called the Lewis acid and or Lewis base, okay? So what we can also call these are nucleophiles and electrophiles. A nucleophile is something that likes positive charge. An electrophile is something that likes negative charge, okay? So a Lewis acid is a substance that can accept a pair of electrons, okay, to make a new sigma bond. So basically, your Lewis acid is the electrophile. It's looking to reach out and accept electrons to make a new sigma bond. Write that down. Lewis acid is a substance that wants electrons to make a new sigma bond. Okay. New sigma bond. Okay. So that means on the opposite side of that, we have a Lewis base. And a Lewis base is something that wants to donate a pair of electrons, okay, to make a new sigma bond, okay? So in that case, the Lewis base tends to have a lone pair already available somewhere on the Lewis dot structure that we'll see. And in the Lewis acid, it doesn't necessarily have to have a positive charge, but it has to have less than an octet to make it partially positive. Okay, so let's look at that and define those 2 things just in these 2 compounds here. So here we have water. And you're thinking, well, water, that can be an acid or base, right? And that's true. And the reason that we're calling it the Lewis base here is it's the one that's going to be giving the electrons to the boron to create that new bond. Okay. Now, boron here, it doesn't have a positive charge on it, but it does not have an octet either. So because it doesn't have 8 electrons around it, it only has those 6 electrons that it's sharing with the fluorines, it will act as to accept those electrons, and it forms the new bond here. Now, most of the time in acid-base reactions, we have an equilibrium, okay? And the equilibrium is the rate at which it goes in one direction versus the rate at which it goes in the other direction, okay? So in the case of where you're forming a sigma bond, the strength of that sigma bond will control the back reaction, and the force of having the electrons being attracted to that partially positive charge of the boron is the driving force for the formation of the bond. Okay, so Lewis acid accepts electrons. Lewis base donates electrons. Let's look at another version of that here. And we're also going to call them nucleophiles and electrophiles here, because what we'll see here is that we're using one thing that has a negative charge to attack something else, okay? So it is attacking that. And in this case, we're using the electrons on the sulfur as our Lewis base. Those electrons are going to reach out and attack this carbon. Now, why did it want to attack that carbon? Well, of all the bonds on this carbon, you have carbon-hydrogen bonds and that carbon-bromine bond. The carbon-hydrogen bonds are non-polar, okay? But the carbon-bromine bond is polar, and it's more negative on the bromine side, meaning that carbon was partially positive, and that's the driving force there, is that we had our base come in and attack the partially positive, but it didn't have a charge, side of this equation, and then it can go into that direction to form our new sulfur-carbon bond. So our base gave electrons to form a new sigma bond. Now, once we get to the other side of the reaction, now our bromine has all the electrons and it has a negative charge. It is now the new Lewis base. And so now that it's the new Lewis base, we can actually have it drive the reaction in the other direction. So what's going to decide which way these go? Whichever thing is the stronger nucleophile, and we'll talk about why and how we can discern what the stronger nucleophile is. So the four things to remember on this slide is nucleophile, electrophile, Lewis acid, Lewis base. Okay. Now, so this is a new acid-base concept for organic chemistry. And we use this because not everything has a hydrogen on it to transfer. Not everything can be assigned as a traditional acid, as we would call an areneous acid. It has to have water. But we do have things that do act as what we call Bronsted-Lowry acids and bases. So that's the next definition we need to talk about. So in the Bronsted-Lowry acid and base theory, this still falls under the rules of Lewis acid and Lewis base. But in the case of Bronsted-Lowry, we do transfer a proton, but water is not required for this reaction. Okay, so we can transfer protons amongst organic compounds. Okay, in the classical Arrhenius definition, water is required for the definition. We have to step up way a little back from that because water is not always miscible with organic solvents. So we have to have a new definition. And our new definition is Bronsted-Lowry acid. An acid, just as what you would imagine, is one that can donate a hydrogen. Okay. Now it's called a proton. And I want to make it very clear, you don't actually have a free proton ever in the system. What you have is the electrons are reaching out, grabbing that proton away from, grabbing that hydrogen away from the other bond and leaving those electrons behind. It's never a free proton. It's the electrons are being transferred from one compound to the next. So the opposite of that was what we would be calling the Lewis base, Bronsted-Lowry base. And the Bronsted-Lowry base is the thing that can accept that proton. Okay. So just as in most acid-base reactions, there's an equilibrium associated with that. So let's look at that in a little more detail. So on this side right here, we have acetic acid. Okay, it's a carboxylic acid. It has one hydrogen that can transfer. Okay, and this is a fairly acidic acid. And we'll talk about the scale of acidity in a minute. And when we react it with the Bronsted-Lowry base here, it's the base because it can accept a proton. And this is the acid because it can give a proton away. Once we do that, the acid now doesn't have a proton, but it can accept a proton. Okay, so we call that the conjugate base. The acid always turns into the conjugate base because now it has a charge and can accept a proton to go back to its neutral state. So a Bronsted-Lowry acid always becomes a Bronsted-Lowry base after transferring its proton. Okay. So let's see what happened to the base then. If the base had a negative charge and used those electrons to make that new sigma bond, just like a Lewis base would, and we grab that proton and it is now protonated. Okay, it now has a proton. It has an acidic proton. And so it has become our conjugate acid. This should say conjugate acid. Acid. Okay. So a Bronsted-Lowry acid becomes a conjugate base after it transfers the proton. A Bronsted-Lowry base becomes a conjugate acid and it after the transfer, and it now has a proton it can transfer. Now, that means that that reaction can go back and forth. It can go in one direction or the other, right? So it has an equilibrium associated with that. So how do we know which side to go on? Well, we have to look at the strength of the acid on this side of this reaction and then the acid on this side of the reaction. And you always want to go to the weaker acid. So let's talk about that a little more. Okay. Why are these so big? There we go. All right. So whenever we have an equilibrium, the stronger base always pulls off the proton. So whatever solution, if we have a mixture of bases, the one that's the strongest, the base is the one that's going to win. Okay. And the rate of the reaction is shifted to give us the stronger base. Okay. So in this case here, in a relative sense, we can imagine that our hydroxide here is a stronger base than our carbonate ion. Because hydroxide seems to be much harder, much stronger than the acetate ion. But how do we know for sure? How are we going to figure out which way this equilibrium lies? Okay. So, but the general concept is that the reaction forward versus the reaction back means that we want to have the weaker acid and the weaker base on our products side of the reaction. So if this side is our product side, the equilibrium will be shifted this way if the two conjugate bases, if the conjugate base and conjugate acid are weaker than the two components on the other side. Okay. So imagine, you always want to kind of reach, it's like energy falls downhill. So you have a strong acid, strong base, they're going to react to make a weak acid, weak base. And it's always going to go in that direction. Okay. So how do we figure out that? Well, it turns out most of the time we actually just measure this. And we measure this and we have a ratio of the concentration of the acid times the concentration of the base over the concentration of the concentration of the hydronium ion, the concentration of the conjugate base, divided by the concentration of the acid. Okay, this gives us our equilibrium constant for our acid. Okay, and these numbers can be very large. Okay, so to help kind of make it easier for us to understand those numbers, what we do is we actually take the log of this ratio and we end up with what we call the pH. That's what this is right here, the pH or something. So we also call that the pKa. Okay, so pKa is the log of the Ka, or the acid equilibrium constant. Why is this important? Okay, because when we start looking at our tables of acid and base strengths, what we're going to see, I'm going to answer your question about which is weaker in just the next couple slides here. What we have to do is we're going to start comparing the pKa's of these values. Okay, by comparing pKa's, we're going to know which one's stronger and which one's weaker. And the reason we use this is it's a measured number, it's a known number, and it sets on a spectrum from very high acidity to very low acidity. Okay? So the general term here is that if your pKa is really low, and these can even be negative. So if you have a negative number up to 0, we call those very strong acids. And then as you increase that number, as that number goes up from 1 to 50, it starts getting a weaker and weaker acid. So on our pKa scale, the highest number is the weakest acid. The lowest number, including negative numbers, are very strong acids. Okay. Now, that's just pKa's. Let me talk about the other side here. Okay. So we can also do what we call the base equilibrium constant. The base equilibrium constant is the concentration of the hydroxide times the conjugate acid divided by the base. Okay. So wherever that equilibrium lies, we can measure that. And when we take the log of that, we actually get what we call the POH, or what we'd say is like the equivalent to pH is the POH. But If we take the log of that equilibrium constant, we get the pKb, which is the base constant, okay? So in the base constant, that's going to go up and down just like we saw with the pKa's. And so as the value for pKb goes down, including negative numbers, they get very negative, like negative 30, those are stronger. The more negative the number, the below zero, they are very, very strong. As you go above zero, that's where a lot of the organic compounds are, above zero. As you go higher in number, they get weaker and weaker. So we'll see that is a general trend in both scales. The higher the number on the pKa, the weaker the acid. The higher number on the pKb, the weaker the base. And the opposite is true for the two. Now the cool thing is that always the pKa plus the pKb is always equal to 14. Okay. Now you might remember that from Gen Chem when we were talking about if you had a pH and and an OH concentration, you could always back calculate the other by knowing that it was related to the number 14. So if your pH was 7, you know your pOH was 7 as well. Okay. So now we have to get one of these concepts in our head. And what I like to do is I like to focus just on the pKa's. Okay. So what we want to do is we want to take all of our organic functional groups and kind of rack and stack them for acidity, just looking at our pKa's. Because we can tell which side the equation is on by just assigning the acid and the conjugate acid. Because they are related right here in this equation at the bottom here, we're related here, that you don't have to know both, you only have to know one. So we're going to focus on just the pKa and that pKa scale of acidity. Okay, so here's some functional groups as associated by, and we have both the pKa and the pK listed, just so you can see. But what I want us to focus on right here is looking at the pKa's right here of these two things right here. And so when we're looking at the pKa's, that means we're looking at the protonated species on this table, okay? Now this is the table in the book, but I really want to focus on just the protonated species at this time. So what we're going to do is we're going to, so don't look at that side, right? I want to focus just on the pKa. We do not need to calculate any of these things. We will be able to just look at the relative scale on a table and know which functional groups are where, and we will definitely not need to do any calculations. There's like 3 things we calculate in organic chemistry, and they're all like algebra, so don't worry. No calculator part. So let's look at the middle part right here, water. Okay, so when we think about we'll definitely need to know the relative scale of where different functional groups lie on this. And I have a way to help us remember that. Okay, so water here, okay? So water can act as an acid or a base, right? It can accept protons or it can liberate a proton. And so its pKa is is right here in the middle, we call 15, okay? So that's the hydrogen on the oxygen. And so that is the, what I like to say is, let's start with that as the middle and figure out what's less acidic and figure out what's more acidic from water. So what we'll see is just by adding a carbon group to that, oxygen there and make it an alcohol, it really doesn't change the acidity of that hydrogen very much. And so it jumps up a little bit. So it's a little less acidic because the number got bigger, okay? So, but then let's look at something like up here. The next one of really importance right here is the acetylene. We said in our IR that bond between the acetylene hydrogen was different than it was for the alkene, and it's different for that because of hybridization. That hybridization also changes the acidity of that protein. In fact, this is the most acidic hydrocarbon hydrogen we have. Okay, so that's the most acidic hydrocarbon hydrogen. The next most important thing, and I would try to make a small table of the ones I'm circling here, because these are the ones that we'll be using frequently. So water, alcohol, alkyne are definitely need to be in your small table of things to memorize. The next one here is the alkene right here. And it has a pKa of 43. So that's like a lot less acidic than the alkynyl hydrogen. And the last one up here is the hydrogen on any alkane sp3 hybridized carbon is at least 50, sometimes they're a little higher. So this is the least acidic hydrogen we will be dealing with in organic chemistry, okay? So if we want to think about it as our least acidic hydrogen is a hydrocarbon. And think about it, it's very non-reactive, it doesn't do very much, so it can't be a very reactive bond. Okay, so those 5 on that side of the table are very important. Okay, now let's go and think about things that are more acidic than water. Okay, so the first thing we want to think about that's more acidic with water is the acetic acid right here. So acetic acid is our next most acidic thing here, and it has a pKa of 4.8. Okay, now we can vary that by attachments, and I'm going to show you that in a minute. So, but the first thing we want to do is look at here. If we remove this carbon, which can help stabilize or donate electron density to the carbonyl, this hydrogen can't, and it actually becomes more acidic. Okay, so it's more acidic. Okay, and if we remove even more charge with fluorines here, it becomes even more acidic. Okay, and then we're right here is where 0 is. Okay, and so that means any of our classical inorganic acids like HCl, HBr, or hydronium ion are all strong acids. They are all less than 0. Okay, so if I just throw out HI or hydroiodic acid, you're going to say, oh, strong acid, less than 0. So the ones that are circled, right here, the ones that are circled are the ones that you need to devote to memory, because those are the ones we're going to be using time and time again. Okay? So take a screenshot of that. There we go. All right. So let's go on now. So it's all about this relative scale of acidity. Okay. Okay. So here's another scale. Now notice this is backwards. It starts with the negatives at the top, but it gives you the same trend. But the thing I want to show you here is the relationship between acid strength and the conjugate base strength. Okay. So this is a very important part of the system, because when you have a very strong acid and you pull that proton off, it becomes a very weak base. Okay, so they're complete opposites of each other. Strong acid is always a weak base. Okay, but what does that mean if they're always opposites? That means a weak acid is a strong base. Okay, so no, you get the there. Okay, hand raised.
I was just wondering, so if you have like a strong acid and a weak base, the reaction would shift to like the right? Like if you have like a strong acid and a weak base on the reactant side, and then you have like the conjugate base on the product side, it would shift towards the products?
Maybe. No, what we're going to do in one of the next slides here is we're going to compare the pKa, the acid strength of the acid on one side of the equation, and the pKa to the conjugate acid on the other side of the equation. Okay, and whichever is the weaker acid, that's the direction it's going to shift. Okay, so what we want to do is only look at the pKa of the acid and the conjugate acid, or only look at the pKb. I prefer to look at the pKa of these things. Okay, So I'll show that on another slide, but the key on this slide here is that when we have a very strong acid, when we remove that proton, it becomes a weak conjugate base, okay? So when we're looking at these, we can see in our relative term that like water here is in our intermediate scale here. Once this is not very acidic, but so that makes this is a fairly decent base. So all of our natural acids like HBr, HCl, sulfuric, nitric, phosphoric, consider all of those less than 0. Those are all what we consider strong acids. So all of those are like, you know, completely dissociated water. So we call those strong acids. But for organic acids, all of them are positive. Notice all of these have a positive pK. And again, the ones to remember are the carboxylic acid, which is right around 4.5. And so that makes this not a very strong base. Yeah, definitely always use pKa. Then, of course, our alcohol is right here in the middle. Then we have our alkyne, our alkene, and our alkane, which makes this anion stronger than this anion, and this anion is stronger than that anion. Okay, so that's what we're trying to focus on here, is that base strength is increasing as we go in this direction. So strong acid makes a weak conjugate base. A weak acid makes a strong conjugate base. They're exactly, you know, as one increases, one decreases, and they scale exactly the opposite. Okay, now to go to the question about which way does it lie, okay? So when we're determining which way the equilibrium lies, all we need to care about is knowing the pKa of the acid on one side of the equation and the pKa of the acid on the other side. In this case, it's our conjugate acid, okay? So let's look at that experiment again, where we had the acetic acid here, and we reacted it with hydroxide. We know hydroxide is a strong base. That's what we learned in Gen Chem. But now we know how strong our acetic acid is. We have a pKa value. And for organic compound, that's pretty acidic. However, it's not as strong as HCl or HBr because it's a positive number. So we don't care about the pKb. We're not going to look at that. Now let's go to this side. Okay, this was our acid. So this becomes our conjugate base. So we don't have to look at that value either. Okay, we transferred this hydrogen to this hydroxide. This is now our new conjugate acid. Okay, and we know from our table that our conjugate acid has a pKa of 15.7. So what does that mean? Which way is the equilibrium line? Remember, acidity goes by the smaller the number, the more acidic it is, okay? So if we compare this value to this value, 15 is a higher number, therefore it is a weaker acid, which means the equilibrium is going to be shifted in this direction, okay? Does that answer your question, Ashton? I think this is what you were asking about, direct.
Yeah, thank you.
Okay, great. Okay, so the key here is knowing about 5 or 6 of the pKa's for organic compounds in general, and comparing the acid to the conjugate acid, and you'll know which direction the equilibrium will lie. Okay, let's do that again. And we have another, this is a pretty strong base here because it was a pretty weak acid. It had a pKa of 25. So if we have this acetylide ion acting as our base, and we have water acting as our acid, these electrons are going to reach out and grab this. So this is our Lewis base, grabbing this hydrogen, which is our lowest acid, and turning it into neutral acetylene, and we form hydroxide on this side, okay? But again, we don't care about the pKb's, we're not looking at that. Let's look at the pKa of the acid on this side is 15. So that's a middle of the road, you know, that's kind of could be acid, could be base. That's fine. But the pKa of this is 25, okay? So which direction is the equilibrium line? We have 15, which is not a very strong acid, and we have 25, which is a very, very weak acid. Right, so it's going to lie almost entirely in this direction because the difference in those is like 10 points, okay? So the bigger the difference, the more the equilibrium lies in the other direction. Okay. So now we have a way of a relative scale of acidity, and the pKa scale is easy to remember, and we compare our acid on one side of our reaction to our conjugate acid, or the thing that got protonated, the conjugate acid on the other side, and we know which way the equilibrium will lie. Okay? So does that make sense? This is a very good, important concept. Okay? And when we talk about amines next semester, I will bring up the pKb scale because amines act as bases, but this is the most important concept for the first half of organic, and so I'm going to stick it here, and I'm not going to talk about pKbs. Okay, so now that we have this idea, we have a relative scale of how acidic things are. We have about 6 functional groups that we are going to put to memory as their relative area, and we know how to see which way the equilibrium lies. What can we also do there? Well, we can actually change the acid-base strength of a basic thing, of a structure, because it has actual relationships with the connectivity and the electron withdrawing and donating and conjugation. So they actually can change a little bit. How do the pKa's need to be? They even a point will tell you that the most reactions are okay. Let's see. I have a question in the Zoom chat about how different do the pKb's needed for the reverse reaction to be negligible. In theory, all reactions have equilibrium. However, if you can't measure the other component, it's considered negligible. The rule of thumb is about 10, but that is affected by solvent. So it's just a general rule, but it's not actually a hard and fast rule. Okay, so does that answer your question? So if I'm going to ask a question, I'm going to say which direction does the equilibrium lie. I'm not going to say whether or not it's negligible. Because really you have to measure it. And so that's the key there. All right, so.
Dr. Irving, I had another question.
Okay.
On the previous slide, would it be fair for the students to expect a problem like that without the pKa values given?
Just using the known organic structures that we will be using, yes.
Okay.
So things.
Just wanted to make sure.
Yeah. So the organic structures that are circled here that I suggest you know the pKa's, then you should be able to just look at that equation and say, okay, this one's higher than this one, therefore it's going to go in this direction. Yes. So, but don't memorize them all. Just do those, you know, the few that I circled, because those are the ones that we're going to be using the most. Okay, so I said before that we also have this thing called Lewis acid, Lewis base. And so this same kind of acid-base combination helps us understand many, many organic reactions, okay? So let's dive into this a little deeper and look at acid-base strength and how it affects things. Now, in most organic reactions, we don't have water present, right? And so we need to think about if the reaction is in water, water is often not shown because we expect it to go through this concept of the water acting as a base and dissolving the acid to give us our conjugate base and our hydronium ion. Now notice these are counterbalanced right here. And so we typically don't show this in organic reactions, but we need to remember that it's kind of there in the background and sometimes can play a role in our reactions. Okay, so now let me talk about it in the function of Lewis acid, Lewis base. So in the case here, this is what we consider a Bronsted-Lowry base because we are transferring a proton. Okay. But what I want you to look at here is that this, if we called it our Lewis base, has electrons to make a new sigma bond. And this size has something that can accept those electrons. So in the first case here, we have our electrons coming over, and once these electrons start forming that bond around the hydrogen, the two electrons that are in the sigma bond here go back to the other atom. Okay. Again, you never have a proton floating around in space. These electrons start to surround the hydrogen. The other electrons are left behind. And that generates our new bond here. Now, this is reversible because now this is our base and this has a proton that can be transferred, hence the reversibility. Okay. So one of the driving forces here is the stronger base will form a stronger pi bond with the proton, and therefore it will it'll win the tug of war. Okay. So basically, the stronger the bond created, the more it's going to shift in that direction. Okay. So that means that we always have our equilibrium form the weaker acid and the weaker base because we want to form the strongest sigma bond. All right, so let's dive into that a little more. Okay. So the acidity also depends on the stability of the conjugate base. So if you have something that's a nice stable ion, like chlorine or bromine, that means that it can be a more acidic compound because it's not scared to have a charge around it. Okay? The acidity increases with increasing conjugate base stability as well. Okay? So let's say that you have the acetic acid and the acetate ion. That acetate ion, because of conjugation, means that it can stabilize that charge more than if it was just on a regular oxygen, like in ethanol. That means that if we can stabilize that charge over 2 oxygens, that makes it more acidic because that anion is more stable. So look at it that way. The less reactive the conjugate base is, the stronger the acid is. Okay, so when you make something that doesn't, react very much, that means it's going to be a stronger acid, and the equilibrium shifted toward transferring the hydrogen. Okay, so that whole concept of what makes one acid weaker than another has everything to do about the equilibrium constant, which is measured. Okay, and it's all about that bond strength created in that new sigma bond. So we look at the bond strength on the first side of the reaction, right here, and we're thinking about the bond strength, this bond right here, versus the bond strength on the other side of the reaction, the bond strength here, okay? And whichever has the stronger, less polar bond will be the one that is going to give us it's going to be shifted in that direction. So in this case here, we would have to know the nature of our substance that the hydrogen was on, and the stability of this ion here will control it. The more stable that ion is, the more willing it is to give up the proton. The less stable it is, the less willing it will be to give up that proton. Okay. So the stronger the acid, the smaller the pKa. The stronger the acid, the more it's shifted to the weaker acids. Okay. All strong acids make weak conjugate bases. All weak acid make strong conjugate bases. So it's kind of like that, you know, the opposite is the opposite. So a strong acid is the weak base. And so that is, the opposite is the opposite. All right. So what changes one acid to make it more or less acidic, okay? And there are 4 factors that make things more or less acidic than other things, okay? And those 4 factors are the electronegativity and size of the atom. And we'll think about that as, the chlorine versus bromine versus iodine, okay? Those are all similar electronegativities, but they change in size. The second thing that changes is resonance or delocalization of charge. So if you can take that charge and spread it out over 2 atoms or 3 atoms or 4 atoms, it's going to be more acidic because you have less of a charge on any one atom. The third thing we have is inductive effects. And inductive effects means that we can draw electron density or add electron density through sigma bonds. Okay, it's not through space, it's through the sigma bonds. And the last thing that changes it is the hybridization of the atom. And we see that especially in alkynes, alkenes, and alkanes. Excuse me. Okay, so we're coming up close to the end. So let me just talk about I don't want to, okay. I'm going to pick up here next time. We're going to talk about those 4 things that change the acidity. So a strong Bronsted-Lowry acid is more stable. The strong Bronsted-Lowry acid has a more stable conjugate base. Yes. So think about whenever it was an acid on this side of the reaction, it's always the conjugate base on this side of the reaction. If it was the base on this side of the reaction, it's now the conjugate acid on this side of the reaction. Okay. And whenever we're trying to figure out which way the equilibrium flows, we only look at one of those. We look at the acids or the bases. And we'll see that if the acid is stronger on one side than the other, then it's going to be shifted to whatever side has the weaker acid. Okay, does that answer your question? Okay, so we're right here about 10:48. I'm going to open it up to questions. I'm going to go ahead and finish the last few slides right before our group activity on Friday. And if you didn't receive an email about that group activity, tell me, because I've sent it out through, not through Canvas, because some people aren't getting the Canvas one, so I sent it through Outlook. Okay, well, if you have somewhere else to be or something to say, go ahead and start going away. And if you want to stay and talk and have a couple questions, go ahead and stay around for that.
I have a quick question.
Yes.
So the test that's next Friday, you said we just have the 1 hour for it?
Yes.
So it'll time out at an hour?
Yes.
Okay, just double checking.
Yeah. Unless you have an ODS accommodation, and then that will be accounted.
Okay.
You did not receive an, yeah, sorry, Nicola. Yeah, I'll send it to you now. I need to add you to that mailing list. I'm sorry, I forgot.
Thank you, Dr. Irving.
All right, thank you. All right, I'm gonna stop sharing. Away we go.